Hi students, this is Shiva, your maths teacher. You are watching YouTube channel Maths Insights. In today's video, we are going to discuss three important definitions in matrices. The first one is transpose of a matrix, second one is symmetric matrix, third one is skew symmetric matrix. Without making any delay, shall we discuss? The first definition is transpose of a matrix. If you take any matrix, it may be square or otherwise, whatever it may be, then if you interchange the rows as columns and columns as rows, then the resultant matrix is called the transpose of the original matrix. I am taking a matrix A. If you take these as 1, 2, 3, 4, 5, 6, this is a matrix of order 2 by 3. 2 rows are there, 3 columns are there. I want to find transpose for this matrix. Then the transpose of this matrix is written as A power capital T or A power small t or simply A dash also. Its transpose is obtained by interchanging rows as columns. The first row is 1, 2, 3. I am writing it as column, first column. If you see the second row as 4, 5, 6, it will become second column. This is the transpose of the matrix A. If you observe, the order of the original matrix is 2 by 3. 2 rows are there, 3 columns. Now, 3 rows and 2 columns are there. Means the order is reversing. This is the way how to find transpose of a matrix. In compact form, if you want to describe the transpose of a matrix, I am taking A is equals to Aij, whose order is m by n. Then its transpose will become A dash. I am simply writing A dash. Aj means interchanging rows and columns. When you interchange rows and columns, the number of rows becomes columns, number of columns becomes rows. Therefore, the order of this matrix will become n by m. In this way, you can find the transpose of any type of matrix. The properties of transpose of a matrix are very important. The first property says that if you do transpose twice for a matrix, that means A dash whole dash is equals to, if you will get A again. Why? Because you are interchanging, you are writing rows as columns 2 times. Automatically you will get the original matrix again. Therefore, A dash whole dash or A transpose whole transpose will give you again the original matrix. Second property says that A plus or minus B whole dash is equals to A dash plus or minus B dash when A and B are conformable for addition. If you want to find A plus B whole dash, it is enough to find A dash first plus B dash second. Then you will get the same matrices on both sides. But here A and B should be conformable for addition, means they should be of the same order. Then only you can add to any two matrices. The third property says that Ka whole dash is equals to, where K is a constant, Ka whole dash will become K into A dash. Why? Because K is not a matrix, it will not be transposed. Therefore, only for the matrix A we will do transpose, that will become K into A transpose, where K is a scalar. You may write it as a scalar. The next and fourth one is very important. A into B whole dash is equals to. Here the students will get confusion whether it is A dash into B dash or B dash into A dash. Generally they think that A dash into B dash, but that is not correct. It is B dash into A dash. B dash into A dash. Dash is nothing but transpose. But here if you want to find A into B whole dash, A and B must be conformable for multiplication. There is a condition. Always you cannot multiply any two given matrices. If you want to know a detailed knowledge, if you want to get detailed knowledge how to multiply two matrices, you may watch the video which is specially made for multiplication of matrices from the playlist. So A into B whole dash is equals to B dash into A dash, but A and B should be conformable for multiplication. So to generalize this, if you take A1 into A2 into A3 and so on, AN whole dash, you have to start to write from the last matrix, that is AN dash into AN minus 1 dash into and so on, A3 dash into A2 dash into A1 dash. Whatever the number of matrices you multiply first, that result will become equal to writing from the last matrix which are multiplied in the reverse order, then you will get the same matrix. This is the transpose of a matrix. Next we will discuss symmetric matrix. If you want to check whether a matrix is symmetric or not, first of all it should be a square matrix. For square matrix only we will verify whether it is a symmetric matrix or not. The definition says that in any square matrix, if you do the transpose of that square matrix, if you are getting again the same matrix, then that matrix is said to be symmetric matrix. Suppose A is a square matrix. A is a square matrix, and if A transpose is equals to A, then A is said to be a symmetric matrix. But here A should first become a square matrix, otherwise you cannot do we cannot check whether it is a symmetric matrix or not. But transpose can be done to any type of matrix. I clearly said just now. Write it in the compact form. Suppose A is equals to Aij, whose order is n by n or m by m. Number of rows must be equals to number of columns. Why? Because this must be a square matrix. Then if Aij is equals to Aji for all I comma j, you are saying that A dash transpose, this is the transpose, this is the original matrix for all I comma j, then that is said to be a symmetric matrix. What it is saying is the elements above the principal diagonal and below the principal diagonal must be same. You cannot take different elements above the principal diagonal and below the principal diagonal. Why? Because they are saying that A12 is equals to A21. A12 means first row, second column. That element must be equals to the element in the second row, first column. I am taking A is equals to as 1, 2, 3. I am writing the diagonal elements first, whatever the elements you may write, but above the principal diagonal, whatever, suppose 8, 9, 5, those elements should come here also. Why? Because they are clearly saying that A12 is equals to A21, Aij is equals to Aji. This position is 1, 2, first row, second column. So here also second row, first column, A12 must be equals to A21. Here also 1, 3, first row, third column, that should be equals to A13 is equals to A31. Why? Because they are giving that Aij must be equals to Aji, then only A will become a symmetric matrix. This is the example for a symmetric matrix. They may ask you which of the following is symmetric matrix. Clearly verify the upper triangular elements and lower triangular elements. They must be same and they should be in the order 8, 9, 5, 8, 9, 5. If you do transpose for this, that means A transpose is equals to first row writing as column 1, 8, 9, second row 8, 2, 5 writing as second column, third row 9, 5, 3 writing as third column. If you observe, are you getting the same matrix again or not? 1, 8, 9, 8, 2, 5, 9, 5, 3. Therefore, A transpose is equals to A. Then A is said to be the symmetric matrix. In this way, you can verify If you want to take any example, be careful. You may write whatever the elements you want in the principal diagonal, but the above elements and below the elements of the principal diagonal must be same, and they should be in the order also. First note says that if A is a square matrix, then A plus A dash is always become a symmetric matrix. What I am taking, A is a square. A is a square matrix, then A plus A dash is symmetric. If you want to verify, you may verify. How to verify whether a matrix is symmetric or not? First, do the transpose. If you are getting the same matrix again, that is symmetric matrix, otherwise not. So I want to check whether A plus A dash is symmetric or not. I am doing transpose for it. A plus A dash is equals to A dash plus A dash whole dash. You come across the properties of transpose of a matrix. By using one of the properties, I am doing this. That is equals to A dash plus A, which can be written as A plus A dash. Why? Because A dash whole dash is again A. If you do the transpose twice, A dash I am writing as it is. Therefore, A plus A dash is equals A plus A dash whole dash is equals to, you are getting again A plus A dash. Therefore, A plus A dash is symmetric matrix. Second is the maximum number of distinct elements which can be taken in a symmetric matrix or n into n plus 1 by 2. See, here I have taken 3 elements. Those 3 elements must come here. So only 3 elements which are different, and here 3 different. Total 6. You can take maximum 6. You may repeat any element, that will become less than 6, but you cannot go beyond 6, which are quite different. If you take beyond 6, that will not become symmetric. Now in this case, what is the order? Here n is the order of the square matrix. In this case, 3 is the order. Therefore, 3 into 4 by 2, 2 1 ja, 2 2 ja. So 6 elements can be taken as distinct elements in any symmetric matrix. In this case also there are 6. You may take less than 3. If you repeat here 8, again you may write 8. But here distinct elements will become only 5. That is not a matter, but you cannot go beyond 6. If you go beyond 6, that will not become a symmetric. Suppose here is 9, here also 9. If you take 10 here, first of all, this A transpose will not become equals to A. Therefore, it is not a symmetric matrix. Why? Because you are taking 1, 2, 3, 4, 5, 6, 7. 7 distinct elements are there. Therefore, it will not become a symmetric matrix. So, you will go next to skew symmetric matrix, very important. In this also, if you want to check any matrix is skew symmetric or not, that matrix always be a square matrix, then only we can check. A square matrix, suppose A is said to be skew symmetric matrix if A transpose is equals to minus A. Very simple, somewhat slightly different than symmetric matrix. A transpose is equals to minus A. That means if you write it in the compact form, suppose A is equals to Aij, whose order is n by n. Be careful, it should be a square matrix. And if Aij is equals to minus Aji for all I comma j, whatever the elements Aij is equals to minus Aji means, this means the elements above the principal diagonal, below the principal diagonal are same but with opposite sign. And what about the elements in the principal diagonal? If you want to find the nature of elements in the principal diagonal, you have to replace I is equals to j or j is equals to I. Why? Because the elements in the principal diagonal will have A11, A22, A33. The row number, column number are always same. A11 first row, first column. A22 second row, second column. A33 third row, third column. So if I want to know the nature of elements in the principal diagonal, you have to substitute, put I is equals to j. Then this will become aii minus aii. If you take that this side, aii plus aii, this is 0. So this will become 2aii is equals to 0. Therefore aii is equals to 0 by 2, that is equals to 0. So this means that the elements in the principal diagonal of a skew symmetric matrix are always 0. Then you can easily take an example for a skew symmetric matrix. What about the elements above the principal diagonal and below the principal diagonal? You can take them easily. Suppose example A is equals to, so clearly the elements in the principal diagonal are 0. I am taking every time 3 by 3, but you may take 4 by 4 also, 2 by 2 also, 1 by 1 also. Here I am taking 1, 2, 3. As per this condition, whatever the elements above the principal diagonal, you have to take the same elements below also, but with opposite sign. Minus 1, minus 2, minus 3. This is an example for a skew symmetric matrix. Now I will find transpose to it, right? Then transpose means interchanging rows and column. First row written as first column, second row written as second column, third row written as third column. And in this case, if you take minus common from every element, then 0, this is 1, this is 2, this is minus 1, 0, plus 3, this is minus 2, minus 3, 0. See, if you observe, this is a, nothing but, that is equals to minus a. Therefore, A transpose is equals to minus a, means this is a skew symmetric matrix. Very simple. Be careful in taking example for a skew symmetric matrix. You have to take the elements as 0 in the principal diagonal. Now I am going to notes. The first note says that the trace of a skew symmetric matrix is 0. Again question arises, what is meant by trace? Trace is the sum of elements in the principal diagonal. Clearly we discussed that the elements in the principal diagonal are 0. Therefore adding whatever the number of zeros, you will get 0 again. Therefore trace of A is equals to 0, where A is a skew symmetric matrix. A is a skew symmetric matrix. Second note says that, okay, if A is a square matrix, then A minus A dash. Previously if A is a square matrix, A plus A dash is symmetric. Here if A is square matrix, then A minus A dash is skew symmetric. Okay, A is a square simply. If A is a square matrix, then A minus A dash is skew symmetric matrix. Okay. Now third note says that it's very important also. Any square matrix can be expressed uniquely, means in only one way, as the sum of symmetric and skew symmetric. You come across that if you want to express the square matrix A as the sum of symmetric and skew symmetric, you know that A plus A dash is symmetric and A minus A dash is skew symmetric. But if you do simplification, you will not get A. So to get A, you have to multiply with 1 by 2 here also, here also. If you see half A dash minus half a dash will get cancelled. Half a will become full a. That means a you will get back again. In this way you can express a as the sum of symmetric and skew symmetric matrices. Okay, this is the video today. I hope this will become helpful to you. If you think like that, please do subscribe to my channel, share it, like it, and we will meet again in the next video. Until then, have a nice day. Thank you very much.